In this video, we're going to start talking about series. Now, up to this point in section 9.1, we were talking about sequences. Now we're going to shift gears a little bit and talk about series. So if a sub n is an infinite sequence, then the sum from 1 to infinity of a sub n, which is a sub 1 plus a sub 2 plus a sub 3 all the way past a sub n to infinity, is called an infinite series. And the numbers a sub 1, a sub 2, a sub 3, so on and so forth are called the terms of the series. Now, to find the sum of an infinite series, if this sum exists, we want to consider the sequence of partial sums listed here. So this is a sequence of partial sums of the series. So s sub 1 would just be the first term, s sub 2 would be the sum of the first two terms, s sub 3 would be the sum of the first three terms, all the way down to s sub n, which would be the sum of the first n terms. So you can look at this as defined recursively, where s of n is equal to s of n minus 1 plus the next term a sub n, or you can look at it in its summation form, the sum from 1 to n of a sub I. For the infinite series, the sum from 1 to infinity of a sub n, the nth partial sum is the s of n, which is, of course, the first sum of the first n terms. If the sequence of partial sums s sub n converges to s, then the series from 1 to infinity of a sub n converges. The limit s is called the sum of the series. But if that sequence of partial sums diverges, then the series diverges. So when it comes to series, there are two basic questions. Number one is, does the series converge or diverge? And number two, if it does converge, what is its sum? Now this example just wants us to find S1, S2, S3, and S4 for this series. So this is our a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So S1 is going to be a sub 1, which is 1. S2 is going to be 1 plus 1/4, which is 5/4. S sub 3 will be 1 plus 1/4 plus 1/9, which gives me basically 5/4 plus 1/9, or 49 over 36. And S sub 4 is going to be 1 plus 1/4 plus 1/9 plus 1/16. I'm just going to the next term in the list. And that gives me 205 over 144. Now it's not as bad as it sounds, because once you found S3, all you would have to do is take that number and add 1/16 to it to get to the next one. Now this particular problem says find the nth partial sum of the series from 1 to infinity of 1 over n minus 1 over n plus 1. So with one like this, I'm going to look at a couple of terms and see what happens. So s sub 1 would be just a sub 1, which is going to be 1 over 1 minus 1 over 2. S sub 2 is a sub 1 plus a sub 2. So that'll be 1 minus 1/2, that's the a sub 1, plus a sub 2, which will be 1 over 2 minus 1 over 3. So you may notice that this cancels in the middle, and I just get 1 minus 1 over 3. S sub 3 will be a sub 1 plus a sub 2 plus a sub 3. So that's going to be 1 minus 1/2 plus 1/2 minus 1/3 plus a sub 3 will be 1/3 minus 1/4. So again, the 1/2s cancel, but also the 1/3s cancel, and I get 1 minus 1 over 4. So hopefully you can see the pattern that's going on here. If I were to find S of n, the nth partial sum, this will be 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, all the way down to, well, if we want to go all the way to a sub n minus 1 would be 1 over n minus 1 minus 1 over n. And then a sub n would be 1 over n minus 1 over n plus 1. So this one's going to cancel. This one would have been canceled by the term before it, and it turns out everything cancels except for 1 minus 1 over n plus 1. So that would be the nth partial sum of this particular series. This series is a special type of series. It's a telescoping series. So the idea is that it puts all of these different terms out here, but they end up being canceled. They don't necessarily have to be canceled by the very next term in the series, but eventually they will be canceled. This example says to rewrite the series, the sum from 1 to infinity, 3 over 9n squared minus 1 in a different form. So what I'm going to do is I'm going to try and see if I can turn this into possibly a telescoping series. So I'm going to take 3 over 9n squared minus 1. I'm going to factor that and make that 3n minus 1 times 3n plus 1. And I'm going to try to find a partial fraction decomposition. Now you know how to do this from chapter 8. I'm not going to go through that whole process with you, but it decomposes to the following. If you follow through with partial fractions, you would get negative 3 halves over 3n plus 1 plus positive 3 halves over 3n minus 1. So I'm going to say that the sum from 1 to infinity of 3 over 9n squared minus 1 is equal to, let's take the 3 halves just out because we can factor it out of everything. I'll have 3 halves times the sum from n equals 1 to infinity of, if we put the positive one first, we'll have 1 over 3n minus 1 minus 1 over 3n plus 1. So if I'm going through and listing out some terms, s sub 1 would be a sub 1, which will be 1 half minus 1 fourth. S sub 2, a sub 1 plus a sub 2 will be 1 half minus 1 fourth, plus, when we plug in a 2, we get 1 fifth minus 1 seventh. S sub 3 would be 1 half minus 1 fourth plus 1 fifth minus 1 seventh plus 1 eighth minus 1 tenth. Now from what I'm seeing, it doesn't appear that anything's actually going to cancel here. So S of n then you can't really find a closed form for. So this is really all we can do is break this down into these parts. So just because you can have a fraction minus a fraction, it doesn't necessarily mean it's going to be a telescoping series. You should just be aware that sometimes it can break down to something that's going to cancel out, but it doesn't always do that. Another special type of series are the geometric series. This is the sum from n equals 0 to infinity of a times r to the nth power. And you can think of this as a plus ar squared all the way down to ar to the infinity power, if you will. It's almost like a polynomial in R, except that a is the same for every term and you're going to go to the infinite power. So it may look similar to that, but it's not exactly the same thing. So this is a geometric series with a ratio r where r is not equal to 0. And depending on what the value of r is, it's going to have some interesting properties. So a geometric series with a ratio r is going to diverge whenever r is greater than or equal to 1, when the absolute value of r is greater than or equal to 1. And if the absolute value of r is between 0 and 1, then the series converges specifically to the sum a divided by 1 minus r. Okay? Now this is important to note. It doesn't say that r has to be less than 1. It says that the absolute value of r has to be less than 1. So if you happen to have a negative r, it can still converge. Okay? So think about why this would be the case. If you are multiplying repeatedly by a fraction, and that fraction happens to be a fraction that has an absolute value between 0 and 1, then the more times you multiply by that fraction, the smaller it's going to make your entire term. Okay? So it's basically just going to have it's basically going to decrease what you're adding every time. Okay, so let's do an example. It says evaluate the sum from 0 to infinity of 5 over 3 to the nth power. And I'm going to bring the 5 out. So I'll have, or I might even write it as the sum from 0 to infinity of 5 times 1/3 to the nth power. Because 5 is not being raised to the nth power, so we're going to assume a numerator of 1. 1 to the nth power is 1, and then we get that 3 to the nth power in the denominator. So this is a geometric series. A is equal to 5 and R is equal to 1/3. And you can see that the absolute value of R is less than 1. So we know that this converges. And we know that it's going to converge to 5 divided by 1 minus 1/3, or 5 divided by 2/3, which is going to give us 5 times 3/2, or 15/2. So it converges to 15/2. Another type of problem you might see is something that says, like this one, write the repeating decimal 0.45 repeating as a geometric series. Now you know that 0.45 repeating basically looks like this. We just repeat 45 over and over again forever and ever and ever. And if we take that pattern as individual terms, like if I were to write this as 0.45 plus 0.0045 plus 0.000045, and so on and so forth, you can see that eventually we would fill in all of those 4 5s as we added those together if we just kept doing this forever and ever. So what I'm going to do is I'm going to convert these to fractions. I'll have 45 over 100 plus 45 over 10,000 plus 45 over, well, let's see, that gives me 6 zeros, so 1,000,000, and so on and so on and so on. And I'm going to write that as powers of 10. So that'll be 10 squared plus 45 over 10 to the 4th power plus 45 over 10 to the 6th power, so on and so forth. Okay, now one thing that I can do here, I notice all of these have 45 over 10 squared in common, so I'm going to factor that out. And I would have 1 plus 1 over 10 squared plus 1 over 10 to the 4th, and so on and so forth. And I'm going to observe that I could write 1 as 1 over 100 to the 0 power. 10 squared is 100, so I could write that as 1 over 100 to the 1st power. 10 to the 4th, I could write as 10 squared, or 100 squared. So I could write this as a geometric sequence. And we could write it as 45 over 100 times the sum from n equals 0 to infinity of 1 over 100 to the nth power. And you could put the 45 over 100 on the outside or on the inside. It doesn't really matter. Because this is a geometric series where r is equal to 1 over 100, which is less than 1. So this will be a 45 over 100 divided by 1 minus 1 over 100. So that's 45 over 100 divided by 99 over 100, which is 45 over 100 times 100 over 99, or 45 over 99. Now it did ask us just to write it as a geometric series, so this is it as a geometric series. This is why 0.45 repeating is equal to 45 over 99. Lastly, let's look at some properties of infinite series. If we let a sub n, the sum of a sub n, and the sum of b sub n be convergent series, let a, b, and little c be real numbers. If the sum of a sub n is equal to a and the sum of b sub n is equal to b, then the following series converge to the indicated sums. You can multiply through by a constant multiple. This is just the same thing as distributing c over every term. You can add the two convergent series together and get the sum of their values, or you could subtract them as well. Theorem 9.8 says the limit of the nth term of a convergent series. If the sum from 1 to infinity of a sub n converges, then the limit as n approaches infinity of a sub n is equal to 0. Now, you have to be careful with this statement. This says if your series converges, then the limit of the sequence of terms is equal to 0. Okay? This does not say that if the limit of as n approaches infinity of a sub n equals 0 is equal to 0, then the sum converges. What it does say is that if this limit is not 0, then this series cannot converge. It has to diverge. So these two statements are what we call contrapositives of each other. Okay? If the limit of the nth term of a series does not converge to 0, then the series must diverge. It makes logical sense because if a sub n does not converge to 0, then when you add the next term, your sum keeps changing. It could either get bigger or smaller. So the whole sum can't converge. But this is very, very important. The nth term test can never be used to show convergence. It only can be used to show divergence. So if you say this series converges by the nth term test, you are automatically 100% wrong. You can never use the nth term test to confirm that a series converges, only to show that it diverges. Okay? So here's an example of where you might use it. It says use the nth term test to show that the series from 1 to infinity of 2 to the nth power diverges. So here I would say a sub n equals 2 to the nth power because that's what we're taking the sum of. The limit as n approaches infinity of 2 to the nth power is equal to infinity, which is not 0. So by the nth term test, we can say that the whole sum diverges. This question says, can you use the nth term test to show that the series from 1 to infinity of 1 over n converges? Why or why not? The answer here is no. The nth term test can never be used to show convergence. Now you're going to want to use it because you're going to look at this and say, well, the limit as n approaches infinity of 1 over n, that's equal to 0. And you're going to want to say that it converges, but you cannot do that. It is not logically sound and it's not correct. We'll talk about how to deal with this in the next section.